Hello, everyone. Thank you for attending my presentation. My name is Daequan Peele, and my project for this summer with Qile from NC is twirling coherent errors via non-ideal teleportation. So for a problem statement, can non-ideal teleportation circuits be used to twirl coherent errors on a single qubit? There are a couple of words in there that aren't going to make sense now, but I plan to explain them as we go through the presentation. So first, we're going to focus on the difference between coherent and poly errors. Poly errors are an error in measurements due to a probabilistic application of a polygate, that being I, X, Y, or Z, to a qubit. These are very well studied in quantum error correction, and when poly errors happen in a quantum computer, we have in literature discovered ways to account for this. Coherent errors are essentially anything that isn't that. The coherent errors that we're focusing on for the sake of this project are errors in measurement due to an unexpected unitary operation on a qubit. These are not very well studied in quantum error correction. However, there is an algorithm to convert coherent errors such that the expectation is that of a poly error. This is called twirling. I'll continue to expand on that later. But in order to fully get that, we need to understand how coherent and poly errors differ as they compound over time. So here I have a graph of how the expectation values of this angle applied to a base state 0 evolve over a certain amount of rounds. And so what you can essentially imagine is happening down here in this graphic is that you have your, so you have your error. So you have your input qubit, right? And then it counters an error. That's going to change the expectation value. And then it counters another error. And then it's going to encounter another error. And this is for every round that you run the simulation. So this is going to compound. What does that compounding of the error look like? It looks like this oscillatory sinusoidal wave. And so essentially, what we're going to focus on for the sake of this project is that if you look at the first half of the period, the expectation value decreases quadratically. This is, in computing terms, pretty fast. And this is not ideal because when you're talking about errors, you don't want your errors to grow quickly. And so we are going to move to a poly error. And so this is, there's an error here and another error, right? There's an error in the graph that's shown. It's not like the correct angle to make the comparison between this and the coherent graph, but the idea is that a poly error over time. And so here we have the same example where you take your state initial qubit, goes to a poly error, and then goes to another poly error, and it goes to another poly error. And this is how this is going to compound over a certain amount of rounds. And so here the expectation value exponentially decays to 0. And so if we focus on, if we just look at this kind of initial between rounds 0 and 10, you can almost say, I should put a trend line up here, but you can kind of say that the decay is linear, which is slower than quadratic, and this is good. And so this is very useful and good for quantum error correction, as I said before, because we can account for that decay. And so in order to make coherent errors behave like poly errors, we need to use a thing called poly twirling. And in order to twirl things, we use this object called a density matrix. A density matrix is defined as the outer product of a qubit. And a density matrix is essentially representative of a collection of states that a qubit can be in. And so what this means is that if there is a probability that a qubit can be in a specific state, you sum all of that, and that is your density matrix depicted as rho hat, or rho hat, rather. And so let's say you had a qubit that had a 1/2 chance of being in a 0 state and a 1/2 chance of being in the 1 state. Your density matrix would look like so, where on the diagonal, you would have the probabilities for the qubit to be in either state. And so with density matrices, you can apply operations to them, but when you do apply an operation to a density matrix, you need to multiply your observable on both sides, where on the right side you have its dagger. And so this is going to go into polytwirl, like the function of it. We have our density matrix rho, and we perform an operation. This is the first polygate, and that polygate can be one of any four, right? I, X, Y, or Z, and so it's the summation over 4. And so then you're going to apply your error. And so if you think back to the boxes that I had showed previously, where it is like poly, 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 or error, error, error. This time it's poly, error, poly. This is the idea of polytwirling, where you sandwich a coherent error with polygates. And so this is the start of a sandwich, where you have like the first polygate and an error. And then this is the end of the sandwich, where you have a polygate and then an error and then another polygate. And so if you have your error defined as the potential for applying I, X, Y, or Z, then it can be shown that the channel, I guess, or the representation of what gate you choose for each like step, or the P, epsilon P, is the potential where A mod of A squared, mod of B squared, mod of C squared is the probability of choosing the I row I, where at this point rho has like ingrained the error into itself. And so here we have a polygate twirling an error in the middle, and then another polygate. And so this is just a case, this I row I case. There's also the X row X and the Y row Y and the Z rows. And so that is because of the fact that we are probabilistically applying a polygate, and because the probabilities are A squared, B squared, C squared, this is the definition of a poly error. And so we have moved from coherent errors and twirled them into poly errors via this math. And so previous poly twirling method requires like the addition of like random gates. And so like you need like a P, a epsilon, and a P in order for it to twirl. However, this is not absolutely necessary. In fact, there is a common quantum error correction approach where a following circuit that I'm about to show you appears just by way of correcting the error. And it's called a teleportation circuit. This is a rough example of a teleportation circuit. This is another one. And these circuits, the, I guess, result of using a teleportation circuit is applying a polygate to a input qubit probabilistically. And so to explain the teleportation circuit, you have a input in ancillary qubits, and then these go through a C0. And then in this case, where you use 0 as the ancilla, you would measure on X, and this expectation value would be either -1 and 1. And as a result, your input qubit kind of teleports into the information from the qubit. This is what I mean by teleports, is applied with a I gate in where the result of the measurement is 1, and a Z gate where the result of the measurement is -1. This is similar to this other gate where instead of using zeros and so we use a plus, and now we are measuring on Z and we have I or X. And so here we have kind of a simulation of a teleportation poly chain. The one thing of note is that in order to fully twirl a qubit, you need to alternate between having I and Z and I and X. And so here you have, once you have like IZ on like the first and then IX on the bit, then you have a full set of polys where you can fully twirl an error. And so what this means is that in a decently long error chain, there will be errors that are not twirled. So this one's twirled here with the silver gates. This one down here is twirled with the silver gates, but this one is not. And so with that, I did some numerical simulations and I used another math concept called fidelity, where the fidelity is where U is the product of all like gates you apply to a qubit. So you just take all of it. And then it is representative of, it has a similar use of like expectation values in the previous graph. And so as you like deviates from the identity matrix, the fidelity will reduce like from 1. And so from here, we can see that using teleport twirling sequence, you have a similar exponential decay as you would with polytwirling. This is a proof that teleport twirling is an effective way of, or not teleport twirling, but twirling via teleportation circuits is an effective way to twirl qubits. And so here I have a graph that compares the teleport twirling phenomenon with how it would perform if you were to twirl every other error and how it would perform if you were to twirl every error. We notice that it is just about infinite. And so with the non-ideal part, and this is the final part of the background of the problem statement. So here we have, I had said that with it applying I or Z in a teleportation circuit at like 50-50 chance. If there's an error in how the teleportation circuit is like it's actually constructed, like if something happens with the way that C naught happens, or if there's like an error in between the teleport circuits that's not supposed to be there, you can have it apply I or X or I or Z at different rates that are not 50-50. And so these evolve in a different way. And eventually you can get to the point where, for example, in this graph, the probability of X is like decently high. The effectiveness of twirling via teleportation actually is not as effective as if you were to just twirl every other error at some point over time. And so that is the, I guess, extent of my research. The further results would be to quantify how quickly that deviation from 50% will cause a coherent error, and to systematically study that deviation, and to, I guess, summate my results. Ideal teleportation circuits can twirl coherent errors, and as teleportation circuits become increasingly non-ideal, coherent behavior resurfaces. And that is seen with the fact that this exponential graph kind of dips back up as if you're like swoop, which is strange. This concludes the presentation. My GitHub with my incredibly clean code. And I think thank you.
Any questions?
Hi, great talk. Can you explain where exactly the poly twirling is being applied, like before or after that teleportation circuit, or within that teleportation circuit?
In its teleportation circuit. So if we go here, granted I could have done a better way of like picturing it, but if you imagine that this was just like a basic poly twirling sequence, and it would be P, epsilon, P, epsilon, P, epsilon, P, epsilon, where each P is a poly gate. So the gist here is that the result of a teleportation circuit, T, would be either applying I or Z. And then here, the result of applying a teleportation circuit would be I or X. And so you don't get like the full set of polys or missing Y until you have like at least IZ and IX. So like if this was IZ and this was also IZ, then you wouldn't properly like twirl this error. And so that's why you have to alternate. But the main difference between this and I actually have, I didn't think I would use this, but appendix. If you compare this to like a normal poly twirling sequence, that's just like a concession that is made by the definition of the teleportation circuit. That answers the question.
Yeah.
Question?